Hello, everyone. It is October 7th, and it is 1:36. And I'm going to go over chapter 6, which is not in your exam on Wednesday. And if you have any question, please let me know in the lab. I'll send you we are going to start the exam on Wednesday at 8:30. And please bring your Scantron with you. And until 8:30, until maybe 9:30-ish. From 9:30-ish, you don't need, it's only 50 multiple choice question. You don't need more than an hour, but if you want, you can stay and take the exam until 10 o'clock. I would like to collect the exams. And then from 10 to 11:30, all of the slides, models, everything for the lab is going to be there. And so I forgot to email. I should write it down on my list. Email. Okay. Any question? Anything I should know? No, there is nobody here. Great. Love it. No, I'm just kidding. Okay, the chapter is about energy and metabolism. Energy, the definition of energy, according to your textbook, is the ability to do work. That's the definition of energy. Metabolism is combination of anabolism and catabolism. That's what metabolism is. Anabolism and catabolism. Then what is anabolism? Anabolism, it means building up. Anabolic steroids, you've heard of that? Anabolic steroids, building up. And catabolism, it means breaking down. So the food that we drink, eat, that goes through breaking down first inside of our body, and then they are going to be put together based on the molecules of my body. Molecules of my body are different than the molecules, enzymes, proteins, whatever you want to call it. I'm saying molecules. The macromolecules, right? The polymers of my body is different than the plants I eat, different than the animal I eat. I hope I'm making some sense. So that's what metabolism is. This is what is happening in the lecture, all of these today, which I will go over all of them. Please study them, look at them. So before we go to talk about anything else is the flow of energy, thermodynamics. So law of thermodynamics, there are two laws. Later on or sometime in your life, you will come across it. Please pay attention and learn it. You probably learn it in physics and chemistry. And here we go in biology again. You have to know these. Please know it. Okay. A branch of chemistry concerned with energy and changes. It could come up in physics as well. But cells are governed by the laws of physics and chemistry, as I said. Okay. Capacity to do work, two states, kinetic energy of motion, and potential energy stored in, and I'll show you some pictures in a minute. Many forms, mechanical, heat, sound, electric current, light, radioactivity, all of these are the different types of energy that we are talking about. Okay, you guys, these things are not in your notes, the last PowerPoint. Make sure you take a note of them. I come to these PowerPoints to make up the questions for your quizzes and exams. Make sure you study these. So heat is the most convenient way of measuring energy. Yeah, 1 calorie is heat required to raise 1 gram of water 1 Celsius. So if in a jug, I put some water, only 1 gram. 1 gram of water is very small, very little. That's what they say, 1 liter of water. To increase it 1 Celsius, then you spend 1 calorie to raise, and you put the thermometer in there, put the thermometer in here, and increase the temperature from 25 Celsius to 26 Celsius, for example. That's the amount of energy being used is 1 calorie. Because 1 gram is so small, they say, okay, 1,000 grams, which is equal to 1 liter. Okay, so a calorie on food labels with capital C is actually kilocalorie, 1,000. Here we go. So the amount of 1 calorie is very small. So when they say you're supposed to eat 2,000 calories per day, that's what they usually, most scientists agree upon. If you're not an athlete, you're not an average person like me, you're supposed to spend about 2,000 calories a day. So they're talking about 2,000 of this 1,000 calories. So 2,000 times 2,000 is it's like 2 million of small calories you're supposed to use a day. I hope you know what I'm talking about. If you don't, please bring it up in the lecture. We'll talk about that. So 1 gram of carbohydrate, it gives you 4 kilocalories. 1 gram of protein, it gives you 4 kilocalories. 1 gram of fat, it will give you 9 kilocalories. And they measured that in laboratories. Okay, and 1 gram of alcohol, it gives you 7 kilocalories. Okay, anyhow, so the difference between potential energy and kinetic energy. Potential energy, when you spend some energy, remember that, going up, that's what most textbooks or some places, not your textbook, you know, do not get into, they do not talk about it. For getting to potential energy, you do spend some energy. And then when you come down the slide, it is kinetic energy. So when you're standing on top of the slide, when you're standing on top of the slide, that is potential energy. When you come down, it is kinetic energy. So Energy flows into biological world from sun. So sun is the ultimate source of energy for all living organisms. All living organisms, even organisms in deep sea that they never see sun. If there is no sun on planet Earth, they will die too. So sun is the ultimate source of energy for all living organisms. Photosynthetic organism, which is next two chapters, the last chapter for this unit exam, it capture this energy. The energy from the sun is captured in the plants, and then we eat the plants, and then of course we are functioning. So indirectly, we are dependent on sun. Stored as potential energy in chemical bonds. Yes, we will talk about that. Breaking the bonds in biology. Anytime you break a bond, you release energy. Anytime you build a bond, you're making these two come together, you need energy, just like climbing up the slide. I hope I'm making some sense. Okay, so breaking bonds between atoms require energy. Energy stored in chemical bonds may be used to make new bonds. Yeah, that is true. But anyhow, remember, those chemical bonds that eventually you and I use, are coming from sun. Sun is the ultimate source of energy. It puts those chemical bonds together. So redox, we already talked about this a little bit. It's coming back. We do need it now. You remember the first exam, I said redox, make sure you know what redox is. Redox is, it didn't come up with second exam material. Now it's a third exam material. It's coming up again. So the ox at the end of it, ox is for oxidation. You know, if I put this pen made up of metal right here, if I put it on outside, rain and storms, it will rust. It is oxidized. So oxygen get into it and it rust. You know, I hope you've seen rusted nails, rusted, I don't know, whatever, something rusty you have seen in your life. It means oxygen got into that metal and became oxidized. So you see it as a rust, okay? Atoms or molecules loses an electron. That is oxidation. Reduction, on the other hand, atoms or molecules gain electron. Opposite of oxidation. Higher level of energy than oxidized form. You remember sodium and chloride at the beginning of the semester? Sodium loses an electron. So sodium is loses an electron, being oxidized. And chlorine is being produced. Okay? Anyhow, so oxidation reduction together is called redox, which is reaction always paired. Okay, so here is a sodium. You remember that from beginning of semester? This is chlorine. Sodium loses electron to chlorine. So sodium becomes positively charged, becomes cation, and chlorine becomes anion. Then let's see the terms. So sodium loses electron. The process is called oxidation. Look. Chlorine gain electrons. The process is called reduction. Now, this molecule has high energy. This molecule has low energy. Then I'd like to do it right now, later on. I don't want to confuse these things to you, but please write it in your notes somewhere. You're supposed to take notes and write notes, right? So this thing right here, this molecule, sodium, is called reducing agent. This molecule right here is called oxidizing agent. So it means it's receiving. This is a reducing agent. So it is, I know the words are opposite of each other, but I didn't do it. I swear I didn't do it. The first law of thermodynamics, we'll come back to that. Your textbooks like to do things a little bit. They would introduce you this, and then it will come together. Hang on, wait. Okay, the first law of thermodynamics says energy cannot be created nor destroyed. So if I have a gallon of gasoline in here, that gallon of gasoline is not created and it's not destroyed. It came from somewhere. That's not, I'm not going to get there. But energy is not created nor destroyed. Energy can only change from one form to another. If this is a gasoline, I put it in my car, the chemical energy in here is switched from chemical energy to mechanical energy. Total amount of energy in the universe remains constant. In the whole entire universe, total amount of energy is constant. Energy is not created, energy is not destroyed. I know it's hard for you to comprehend, it is hard for me too, but that's what the scientists say. Okay, during each conversion, some energy is lost as heat. Yes. When you put the gasoline in your car and you convert the chemical energy to mechanical energy, you drive, then you get from point A to point B, then go underneath of your car and put your hand under the in the exhaust system. Your hand will burn. Don't do that. 3rd degree burn, maybe 4th, maybe 5th degree burn. Don't do that. That is heat. You're converting one form of energy to another form. Some energy is lost. That energy that is lost, usually it comes out as heat. I give you the example of the car. Second law of thermodynamics says entropy, disorder occurs. It means when you are converting one form of energy to another form of energy, first law, one form becomes another form. In between, you're creating disorder in the universe. You're creating entropy, disorder in the universe. So, I mean, I should not ride my car to school. I should use bike. Same thing, different story. No, you should use your car. You should be on time for your classes. But that's the way it is. You're creating entropy. You're creating disorder. Energy transformation proceeds spontaneously to convert matters from a more ordered to less stable form to a less ordered, more stable form, which that sentence, maybe with this example makes sense. You know that in the plants, we do have chloroplast. Chloroplast take the sunlight, and out of the molecules in there, it makes a more ordered glucose molecule. I'm explaining that sentence. Energy transformation. So you're making an order out of a semi-disorder. And then that we eat that glucose molecule. We are converting the energy from one form to another form, from chemical to muscular, kinetic energy. We are creating disorder. We are creating entropy. So order, disorder, order, disorder, order, disorder, thanks to the plants and sun. Sun and plants together are creating orders for us. And then we consume, and we have to. We are creating disorder. Okay, I hope you enjoy it. So entropy is, when you put ice cubes in a body of water, the water, melts. So you're creating disorder, as we talked about it. So there is a free energy. Make sure that's delta G. G is the energy available to do work. H is the G is equal H minus T. H is enthalpy, energy in molecules, chemical bonds, glucose molecule. Their carbons are attached to each other by covalent bond. Covalent bond, it takes more energy to break them apart than hydrogen bonds, right? They're more stable. But anyhow, enthalpy, the measurements of energy in a thermodynamic system. T is absolute temperature, the Kelvin. You studied that in physics, chemistry. T is a Kelvin, absolute zero. Everything in that state, every molecule stops. Even in the solid state, molecules are still moving. In the water, you're moving faster. And in the gas, they're moving much, much faster. But absolute zero, if my phone was in absolute zero, the molecule in here, of course, it will shatter. It will stop working forever if you put the phone, because the molecules, they come to a complete stop. But anyhow, and S, he's giving you each component of this formula. Enthalpy, energy in molecules, chemical bonds, minus absolute temperature times S, which is entropy on available energy. So that should give you the energy available to do work. Delta G, this is important. This is something I'd like you to know. This page, this one, you should know. Delta G. Delta G is change in free energy. If delta G is positive, it means the reaction is an endogenic reaction, just like photosynthesis. Process of photosynthesis is an endogenic reaction. When you add phosphate, you studied this before. When you add one phosphate to two phosphate of ADP, that is endogenic reaction, because you're storing energy. As a result, that is a positive delta G. Products have more free energy than the reactants. H is higher or S is lower. Of course, not spontaneous, requires input of energy. When you want to have photosynthesis to put the molecules together, you need this energy from the sun. When you're putting ADP together with ATP, you need some energy. Okay, the negative delta G, change in energy, products have less free energy than the reactants. Glucose has usually less energy than all of what is happening with the sun. Of course, as I said, is the ultimate source, all of what the sun did to the chloroplast. H is lower, or S is higher, or both. Spontaneous may not be instantaneous, and the process is exergonic reaction. Breakdown of the glucose molecule is exergonic reaction. Breakdown of ATP to ADP and phosphate, it is exergonic reaction. Okay, energy in chemical reactions, right here is reactant, right here is product. Energy must be supplied. Of course, delta G is greater than 0, positive photosynthesis. Delta G is less than 0, cellular respiration, which you did in the lab last Wednesday. Anyhow, let's go. Activation energy, extra energy required to destabilize existing bonds and initiate a chemical reaction. Rate of exergonic reaction depends on the activation energy required. Larger activation energy proceeds more slowly. Rate can be increased 2 ways: increasing energy of reaction molecule, heating. All of this to me is common sense. I don't know what I can ask from this page. Let's move on. Okay, now we are getting to, in chemistry, you study catalysts. In biology, you're going to study enzymes. So for a chemical reaction to occur without any catalysts, you all know what catalyst? Catalyst is a molecule that speeds up chemical reaction and needs lower amount of energy for the chemical reaction to occur. Okay? So here is a chemical reaction, whatever, photosynthesis, for example, for a combination of ADP to ATP, ADP to phosphate, anything. For that, this is how much energy is needed. And then, of course, at the end, you will have product. However, in the presence of an catalyst, a catalyst or an enzyme, you need less energy. For the same thing, product is going to occur. So catalysts, substances that influence chemical bonds in a way that lowers activation energy, cannot violate laws of thermodynamics, cannot make an endergonic reaction spontaneous, do not alter the production of reactant turned into products. Yeah, that's what enzymes or catalysts are. So catalyst and activation energy, again, he's showing us the same slide. Maybe I went there. ATP, you already know that what it is. Primary currency used. That's the money inside of our body. Currency means, you know, the money in the United States is the currency is dollar. Composed of ribose, 5 carbon, adenine, and then chain of 3 phosphate. Key to energy storage. Bonds are unstable. Energy released when broken. ATP breaks down to ADP. It releases energy. We talked about it from beginning of semester until now. ATP, adenosine diphosphate, has 2 phosphates. AMP, adenosine monophosphate, has 1 phosphate. We talked about that cyclic AMP for this coming up tomorrow's exam a little bit. It's a secondary messenger. Remember that? Anyhow. ATP molecule is showing it to you. This is the diagram. This is the adenine, ribose, and 1, 2, 3 phosphates. These bonds can break. And when they break, they release a lot of energy. Usually when this bond release less energy, high energy bonds, it means when this phosphate breaks easier than this phosphate. It is possible. It is possible a DP becomes to a MP, rare, inside of the cells for releasing energy. So ATP cycle, ATP hydrolysis drives endergonic reaction. We talked about that. Coupled reactions results in net minus GT, minus exergonic and spontaneous. As I said, you know, breakdown of ATP to ADP, it is exergonic reaction. Okay, so hydrolysis of ATP drives what he means storing energy in some other molecules. Is supposed to be the way I'm explaining it. I'm saying it's exergonic reaction, not endergonic reaction. But anyhow, coupled reaction results in minus G. If it is minus G, it's exergonic. I'm not sure why he's saying a hydrolysis of ATP drives endergonic reaction. It means I know what he's talking about, but that's very, it is hard to explain for me. But remember, hydrolysis of ATP is exergonic. Photosynthesis is exergonic. Formation of ATP is endergonic. ATP not suitable for long-term energy storage. Yes, that's right. Phosphate bonds are too unstable. Yes, that is right. Fats and carbohydrates are better to store energy. Proteins are not good source of storage of energy. And then cells store only a few seconds worth of ATP. For example, when you run 100-meter dash fast, maybe I'm just giving up some numbers. The first 40 meters use all of the ATP in your muscle cells. Gone. That takes what? 5 seconds, 10 seconds, let's say you're a slow runner like me. It's gone. 10 seconds, it's all gone. The other remaining, you're using your creatine phosphate, which we talk about it in zoology. It's a storage of phosphate. It gives its phosphate to ADP so you can finish the race. But anyhow, so ATP cycle, yes, let's talk about it, see what he's saying. So ATP plus water, energy for endergonic reaction, cellular process. I see what he's talking about now. Remember this sentence? ATP hydrolysis drives endergonic reactions, other reactions, not itself. Right here. When ATP becomes ADP, other cellular processes are endergonic reaction. But conversion of putting ADP and ATP, putting ADP plus phosphate, it is energy from exergonic cellular reactions from other cells. We drive this ATP, and you will see it. You will see breakdown of glucose molecule right here. You end up with ATP. Exergonic breakdown of glucose molecule is exergonic reaction. I talked about it. Cellular respiration. ATP, when it becomes ADP, it causes my muscle to move. Okay. Enzymes, biological catalysts. Most enzymes are proteins. Some are RNA. One enzyme is RNA, but most everything else is protein. Shape of enzyme stabilizes. Now we are getting to enzymes. I hope we are not, okay, 208. We still have some time. Shape of enzyme stabilizes the temporary association between substrates. Yes, enzymes not change or consumed in reaction. That's what it is. When you go to a church and you get married, the priest or the imam or the rabbi make you as a couple. When you come out, you are a couple now. You're not single anymore. What happens to the status of that imam or priest or rabbi? Nothing. He's still married and happily, or he's still single and happy. Nothing happens to his status or her. When you go to a judge and you want to get divorced now, what happens to the status of judge? Judge is single and happy, or he's married and happy. Because you are getting divorced, he's not going to get divorced. He does not change. His status does not change. That's what it is. Okay? So the priest, the judge, they are enzymes. They make chemical reaction occur, but nothing happens to them. Okay, example, carbonic anhydrase, 200 molecules of carbonic acid per hour made without enzymes, 600,000 molecules formed per second with, he's giving you the time that how much, yeah, they speed up chemical reaction very spontaneously with not much of a time. And then of course, you know, a lot of other things that happens. We'll talk about it. I'm thinking about that email I got to send to 9. Okay, so this is, remember, this is an enzyme. Each one of these little blue balls are an amino acid. Remember that? So when this is a substrate, by definition, a substrate is something that enzyme act on it. This enzyme is going to act on this substrate, something that enzyme act upon. And every enzyme and every substrate are specific. We do not have one enzyme for every chemical reaction in our body. We have thousands and millions of enzymes in our body. Do I make sense? I hope. So the place, this is a huge enzyme, right? The place that the chemical reaction occur is called active site. The place that the substrate fits, it fits into the enzyme, it is called active site. This is active site. This is enzyme. This is a substrate. And then when the substrate goes into the active site, the shape of the enzyme changes. The enzyme is like this. When the substrate goes in here, the shape changes. Look, this shape is not same as this shape. Different. This shape is not same as this shape. They call this enzyme substrate complex. Enzyme substrate complex when the enzyme goes in there. Active sites, pocket or clefts of substrate binding forms enzyme substrate complex. Precise fit of substrate to active sites applies stress to distort particular bond to lower activation energy. Yes, induced fit. Yeah. Okay. So one example, for example, a sucrose is a substrate. The name of the enzyme is sucrase. Ase at the end of the word in biology means enzyme. Ase, A-S-E, at the end of the word in biology means enzyme. So when the sucrose, the sugar that you put in your coffee in the morning, the sugar that you put in your coffee this morning, it sits on the enzyme sucrase. And then, of course, it's a disaccharide, exam number 1 material. and then with help of water, it breaks down to glucose and fructose. Glucose and fructose are product. Sucrose is substrate. Substrate, product, enzyme. Active site. So it makes sense. Am I good to go? So forms of enzymes. Enzymes may be suspended in the cytoplasm or attached to cell membrane and organelles. Yeah, they're all over. Multi-enzymes complex subunits work together to form molecular machine. Yes, there could be, there are a few enzymes, very, very, very important enzymes in cellular respiration. It's just a complex of things. It's just not one enzyme as simple as sucrase or lactase. Some people do not have the enzyme lactase. They cannot eat dairy products, lactose. Okay, but anyhow. So some enzymes are, the multi-enzymes complex subunits work together in form of molecular machines. Products can be delivered easily to the next enzyme. Unwanted side reactions prevented. All reactions can be controlled as a unit. Yeah, I don't know. Do not worry about that slide. Non-protein enzymes, ribozymes, you will see it later on. Your textbook wants to talk about it now. That's fine. We'll come back to that enzyme. This is the only enzyme that is not protein molecule. 1981, discovery of certain reaction catalyzed by cell RNA molecule itself. Two kinds, intramolecular catalysts catalyze reactions on RNA molecule itself, and intramolecular catalyst RNA acts on another molecule. So on a multiple choice exam or something for now, make sure, say all enzymes are protein. The answer is no, false. I could ask that back in 1980s, early 80s. I could ask that in a multiple choice question, but now I cannot. Okay. Enzymes functions. Rate of enzyme catalyzed reaction depends on concentration of substrate and enzyme. Any chemical or physical condition that affects the enzyme's three-dimensional shape can change the rate, optimum temperature, and pH. Yeah, very important. There are enzymes in your stomach working fine, perfectly fine at pH of 2, very acidic. If I have this jug full of some kind of acid that the pH is 2, hydrochloric acid, that is in your stomach. If I put my finger in here for 5 minutes, I take it out, there's nothing left but my bones. Very strong acid, but some enzymes work in there fine. You take that enzyme and put it in your mouth, no way that enzyme would work. That's how it is. Temperature. There are enzymes in the bacteria of hot springs of Yellowstone National Park. They're working fine. Perfect. You take that enzyme and put it inside of our body, it won't work because they want that heat. Okay? I hope I made the situation clear for you guys in here. So right here, optimum temperature, human enzymes is for 37, 40 is tipping the point. Okay, optimum temperature for enzymes from hot springs of prokaryote, yeah, it's 70 Celsius. This is all Celsius. Optimum pH for pepsin, it's an enzyme which is in your stomach. It's 2.5, 2.5. The pH of trypsin, another enzyme which comes from your pancreas, it's 6.5, almost 7. You take that enzyme, you put it in your pancreas, it won't work. You take that enzyme, trypsin, and you put it in the stomach, the acid of the stomach destroys that enzyme. This enzyme, trypsin. I hope I'm making some sense. Important diagram. There are quiz questions, exam questions. I'll give you diagrams. You should be able to answer. Okay, inhibitors, yes, enzymes have, let me see, this is important. Yeah, let me stop. It's 2:20. So I'm going to stop here, and we'll do continue this Wednesday after your exam. But I think you should focus on your the week after. We do not have a quiz. We have just a lab practical exam, right? So it is good to study these things. Do not accumulate them, but get ready for your lab practical exam as well. All right, guys. You have a good evening. Have a good rest of the day, and I see you on Wednesday. Bye-bye.